Hey, welcome! Today we're going to jump right into one of the most fundamental tools in all of navigation, bearings. Honestly, whether you're a sailor, a pilot, or you're just trying to figure out a map, understanding bearings is your key to knowing exactly where you're going and how to get there.
So let's kick things off with a simple question. If I asked you to describe the direction to a building, you might say, oh, it's kind of over there past the big tree, or it's sort of northeast-ish. But how do we communicate that direction to somebody else with, mathematical certainty so there's absolutely no room for error? Well, that is the exact problem bearings were invented to solve.
Okay, let's really break this definition down, because every single word here is super important. A bearing is just an angle, but it's a very, very specific kind of angle. There are two rules that you can just never, ever break. Rule 1, you always start by facing north. And Rule 2, you always measure that angle by turning clockwise. Seriously, get those two things right and you are already halfway there.
I love this way of thinking about it. Imagine you're just standing at your starting point. First thing you do, face north, always. Step 2, you just turn, clockwise, until you're looking right at your destination. And that's it. Step 3, the angle you just turned, that is the bearing. It's a simple physical action you can picture in your head.
And here it is, the golden rule. If there's one thing you take away from this first part, let it be this. Bearings are always written with 3 figures. So, an angle of 45 degrees becomes 045. An angle of just 7 degrees, that's 007. And this isn't just about looking professional. It ensures absolute clarity. It prevents any mix-ups, which, is kind of important when you're navigating a massive ship or an airplane.
Okay, so here's our game plan for today. We've got the basics down. Next up, we'll figure out how to get home using back bearings. Then we'll put it all into practice and actually draw a map. And after that, we're going to power up our toolkit with some serious trigonometry to solve even the trickiest navigation problems. Let's do it.
So, knowing your direction to a destination is great, but what about the trip home? This is where a really crucial skill called the back bearing comes into play. It is the absolute key to finding your way back to where you started.
Now really pay attention to these two diagrams here. The one on the left shows the bearing of B from A. See? You start at A, you measure the angle to B. But the diagram on the right shows the bearing of A from B. You're starting at B and measuring back to A. You can see right away they are completely different angles. That tiny little word, from, it changes everything. So the question is, how do we figure out the value of that return angle?
Well, it's actually beautifully simple. Because the north lines at both points are parallel, we can use some basic geometry. And the rule is just this. If your original bearing is less than 180 degrees, you add 180 to find the back bearing. If it's more than 180, you just subtract 180. So in this case, our bearing of 045 is less than 180, so we just add 180 to it, and boom, the back bearing is 225 degrees. It's a wonderfully simple and reliable rule.
Okay, theory is awesome, but let's make this real. Right now, we're going to use what we know about bearings, grab a protractor and a ruler, and actually plot a journey to find the way home by making an accurate scale drawing.
All right, here's our mission. We've got a ship. It sails 20 kilometers on a bearing of 030 degrees. Then it changes course and sails 30 kilometers due east, which, as we know, is just a bearing of 090 degrees. Our job is to draw this whole journey out to scale, and then we're just going to measure the answer to find the shortest way home.
So after all that careful drawing with our protractor and ruler, this is what we get. The shortest path home is exactly 43.6 kilometers. And if we measure the angle from our final spot, the return bearing is 247 degrees. It's just a really cool demonstration of how a simple, accurate drawing can solve a totally real navigation problem.
Now, scale drawings are fantastic, but they're only as good as your drawing skills. For true pinpoint precision, we need to upgrade from a good guess to a perfect calculation. So let's bring in the heavy hitters, trigonometry.
All right, let's open up our trigonometry toolkit. This stuff should look pretty familiar. We've got Pythagoras' theorem for finding side lengths in right-angled triangles, and of course, the classic SOHCAHTOA, sine, cosine, and tangent for finding angles and sides. These are going to be our precision instruments, no ruler required.
Okay, let's put these new tools to the test. A helicopter flies 30 kilometers east and then 40 kilometers north. Now, if you picture that, you'll realize it creates a perfect right-angled triangle. So the question is, what is the exact bearing and distance for the pilot to fly directly back home? So here's the play-by-play. First, we use the tangent function.
the TOA from SOHCAHTOA, to find that inside angle of our triangle. Next, we just add that angle to 180 degrees to get the full bearing all the way from the north line. And finally, we use good old Pythagoras to nail down the exact distance of that direct route home.
And there you have it, a perfectly precise answer. And we didn't have to draw a single thing. The pilot needs to fly on a bearing of 217 degrees for exactly 50 kilometers. That is the power and the beauty of using trigonometry.
But what happens when the journey doesn't make a nice, neat little right-angled triangle? Well, for those trickier situations, we need to unlock the final level of our navigation toolkit, the sine and cosine rules.
Think of these two rules as the master keys of navigation. They work on any triangle you can throw at them. It doesn't matter what shape or size it is. With these, we can solve pretty much any 2D navigation problem you can think of. The only trick is just knowing which one to use and when.
And here's the simple cheat sheet. You want to use the cosine rule when you have a side angle side setup. You know two sides and the angle that's kind of locked in between them. And you use the sine rule when you have a matching pair, a side and the angle that's directly opposite it.
All right, you ready for the final boss? Here's our challenge. Picture this. You're in a lighthouse. You spot a boat 2 kilometers away on a bearing of 070. You watch it for 5 minutes, and then you take another reading. It's now on a bearing of 040. The big question is, how fast is that boat actually moving? This is a classic problem that's going to require everything we've learned so far. Okay, if we sketch this out, we can figure out the angles inside the triangle made by the lighthouse and the boat's 2 spots. The angle at the lighthouse is easy. It's just the difference between our 2 bearings. 70 minus 40 gives us 30 degrees. Then, using our parallel line rules, we can work out the other angles and we find we have a side, the 2 kilometers, and we know the angle opposite it is 40 degrees. We've got a matching pair. This is a perfect setup for the sine rule. We just plug in the numbers, like you see here, and we can solve for the distance the boat traveled.
And now for the final step. We know the boat went 1.56 kilometers in 5 minutes. To get its speed in kilometers per hour, we just need to figure out how far it would go in 60 minutes, right? So we divide by 5 and multiply by 60, and that gives us our final answer, 18.72 kilometers per hour. A really complex problem, solved so elegantly with the right tool. We've gone all the way from the absolute basics of what a bearing is to these advanced trigonometric solutions. You now have a complete, powerful toolkit for describing direction and plotting any course you want. So the only question left is, where are you going to go from here? What journey will you map out next?